All right, we're back. We are on page 29 of math analysis. We just talked about even and odd trig functions, and the way we worked it out was we looked at a table of values, basically, and we were able to use that to figure out that the sine of negative theta was equal to the negative of the sine of theta. Cosine of negative theta equals the cosine of theta, therefore cosine is even. I meant to say that sine was odd back there. And then tan of negative theta equals the negative tan of theta. We kind of brushed through that one pretty quickly, but it's definitely true. The table should hold up if you check your answers there. And so what I always do is I just remember that cosine's even. If you can remember that cosine is even, its reciprocal will be even. So you got cosine and secant are even. Everything else is odd. And you just kind of like don't really worry about it. You just remember cosine's even, everything else is odd. So what I want to do now is I want to show you something that is incredible in my opinion. And it blew, the first time I ever saw this, totally blew my mind. Didn't even know what to do with myself. So here I am claiming that if theta is measured in radians, so this is only true if theta is measured in radians. If theta is measured in radians, then sine, well, no, there's an x. It should probably be theta. But if the angle is measured in radians, so it should be if x is measured in radians, sine of x is equal to the sum from 0 to infinity, 0 to infinity of negative 1 to the n, x to the 2n plus 1, which is like an odd number, 2n plus 1, time over the quantity 2n plus 1 factorial. And cosine has a similar thing. Cosine of x is equal to the sum from 0 to infinity, 0 to infinity of negative 1 to the n, x to the 2n over the quantity 2n factorial. So what I want to do first is I want to write out a couple terms of that just to show you sort of what this summation is doing for you, right? So sine of x. So sine of x is, so we're going to go, it's first we start with n equals 0. If n equals 0, negative 1 to the 0 is 1. X to the 2 times 0 plus 1 is x to the first over 1 factorial. So we just get x, which is why when x is really close to 0, sine of x and x are basically the same thing. You can test that. So try anything between like, I don't know, negative 0.2 and 0.2. Check out the sine of those versus the x value that you're plugging in. See what happens. So that's when n equals 0. When n equals 1, we get negative 1 to the first, so negative. X to the 2 times 1 is 2 plus 1 x to the third, and then over 3 factorial. So it's minus x cubed over 3 factorial. So this is interesting. We have the option. We didn't do it. We could have written this as x to the first over 1 factorial. That would have been totally fine. And now if n is equal to 2, we get negative 1 squared is positive. X to the 5th over 5 factorial. So we're going to have plus x to the 5th over 5 factorial. You start to see the pattern, right? So you can go x to the 7th over 7 factorial plus dot, 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 plus negative 1 to the n, x to the 2n plus 1 over quantity 2n plus 1 factorial, and then plus dot, dot, dot. It goes forever. Okay, cosine. I'm going to do the same sort of thing. So cosine. So notice sine had only odd powers over odd factorials, and then it alternated. We're going to use a calculator to like test some of these in a second. But first, let's do some for cosine. So cosine of x is going to be equal to, all right, so if n is 0, we end up with 1 times x to the 0 is just 1, and then over 0 factorial, which is defined to be 1. So we actually just start with 1. And then if x is 1, we get negative 1 to the first, which is minus x squared, and then over 2 factorial. Already, if you saw it for sine, you kind of see it for cosine here. We're just going to end up with evens over even factorials and alternating signs, plus, minus, plus, minus. So this will be plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, 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 plus we get a negative 1 to the n, x to the 2n over quantity 2n factorial plus dot, dot, dot. Okay, so what I want to do now is I just want to show you on the calculator to kind of like prove that this is true, because The actual math behind it is definitely beyond us right now, but that's not going to stop us from playing around with it. So let's see. I'm going to start off with this. I'm going to define a function that I'm just going to call s of x for sine of x. And I'm going to make it the sum from n equals 0 to, so I can't really go to infinity. So I'm just going to go to like 5, I guess. And then I'm going to type in -1 to the n x to the 2n plus 1 over quantity 2n plus 1 factorial. Okay, so let's see what it says for s of x. Now you can see it's expanding the factorials, right? So 3 factorial, 5 factorial, 7 factorial. Those are where your denominators are coming from. But that's what we wrote on paper, except we didn't expand the factorials. And in fact, it's not really normal to expand them. If you're a human, the calculator, there's nothing you can do. All right, I'm in degree mode, so nothing's going to work. What I need to do is change into radian mode. So I'll do this the old school way, doc 7.2, and then click, go up. Okay. All right, now I'm in radians. Let's see. Let's do the sine of 0.5. And let's do s of 0.5. That's pretty close. I mean, as far as we can see, that's exactly right. It's definitely not exactly right. Let's subtract them, 0.5. This is like a little trick for seeing how close things are. Subtract them, very, very close, right? So let's see how far out we can go. So if I try to do, I'm gonna do two things. I'm gonna do sine of x comma s of x. So then I can just like feed it. I'm gonna do such that, so control equals, go one to the left, do x equals, so like 0.5, it'll give me those values. Let's try 1, let's see how far. Oh, wait, let's do control and then, or control enter. Yeah, pretty good. Let's say 2. Still really good, but you can see it's different there at the end. So like 2, it's not enough, but maybe, remember, I'm supposed to go to infinity and I only went to 5. So the more terms you add, the better this will get. I'm gonna go to 25. Let's see. So control and okay, good. Let's try 3. Yes, let's try 4. Pretty good. Also, we went to the negatives because sine is positive in the first and second quadrants, which is 0 to pi, which is 0 to 3.14. So as soon as I went to 4, I was now in the third quadrant, and I knew that sine would be negative. Let's look at the graph. So we haven't really looked at graphs of these things yet, but there are graphs of the trig functions. So here's sine of x. Okay, now I'm going to graph s of x, which is our sum out to 25 terms, which is really 26 terms because we started at 0. So this, so it looks great. Let me zoom out so that you can see something happens eventually. There it is. Okay, so what is happening here? Well, let's go back to our definition. This definition up here, essentially I'm plugging in 0, 1, 2, 3, all for n. Eventually I plug in 25. When I plug in 25, I get -1 to the 25th, which is -1, x to the 50 plus 1, x to the 51st. So I have a negative odd polynomial. Negative odd polynomials always start high and end low. And if you look, we're starting way up high, we are ending low. And there's no choice. If you don't go all the way to infinity, eventually it's gonna stop matching up and eventually it's gonna start high and end low. Or you could get a positive, polynomial. So let's go to 26, right? So now it's -1 to the 26 is +1, but to the 26 times 2 is 52, plus 1 is 53. So it's a positive odd, so that'll go low to high. Let's go back to the graph. And you can see it starts low and ends high. The only way it matches up forever is if you actually go to infinity, but we saw that you get a really good match really soon, right? With only 5 terms, it was good for, basically probably like -2 to 2, which is like really far. So these work, and cosine would be the same. I don't think I want to take the time to show that right now. I'm going to switch back to the notes. And I want to show you the actual purpose of this. So one is to just introduce you to those. They're incredible, right? So like it's worth knowing, I think, for sure, it is definitely worth knowing, worth kind of like memorizing, having it with you all the time, that sine of x is like basically x when x is really small, and that cosine of x, so you want to go more terms for cosine. Cosine of x is basically 1 minus x squared over 2. Those are great to know. They give you a sense of the shape of the graph. You can approximate things like pretty quickly. So what I want to do, I actually added an extra page here so I could do this. I'm going to use these series to prove that sine is odd and that cosine is even. So on this next page here, and then I'll fill this in. So on this page here, let's fill this in. So here we go. So sine of x, so I remember them, so I'm gonna write them. So sine of x is 1, nope, it isn't. It's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot 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 plus negative 1 to the n, x to the 2n plus 1 over quantity 2n plus 1 factorial plus dot dot dot. Okay, what I'm going to do is I'm going to use this to find sine of negative x. So the sine of negative x is, just replace every x you see with negative x. So it's going to be negative x minus the quantity negative x cubed over 3 factorial plus the quantity negative x to the 5th over 5 factorial minus dot 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 plus negative 1 to the n negative x to the 2n plus 1 over quantity 2n plus 1 factorial plus dot dot dot. All right, so what can we do? Well, all of these are odd powers. So negative x, right? Negative x is negative 1 times x. So negative x cubed is really negative 1 cubed times x cubed. So sine of negative x is negative x. So it's minus negative 1 cubed is negative 1. So it's minus negative. So plus, and then x cubed over 3 factorial. And then the same argument happens here. Negative 1 to the 5th is negative. So it's plus negative x to the 5th. So this is just minus x to the 5th over 5 factorial. Then I'm going to switch that. I'm going to say plus. Now what is happening here? So here we have, you end up with negative 1 to the 2n plus 1, x to the 2n plus 1. But negative 1, 2n plus 1 is always odd. Negative 1 to an odd power is always negative 1. So this is actually just negative 1 times x to the 2n plus 1. But there's still this negative 1 here. So we actually end up with negative 1 to the n times negative 1 to the first is negative 1 to the n plus 1, which means that this just has the opposite signs everywhere. And then x to the 2n plus 1 over quantity 2n plus 1 factorial plus dot dot dot. But that is just take a negative out of everything you see. Negative quantity x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus dot 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 plus. So we're taking a negative 1 out of everything we see. So this goes back to negative 1 to the n, x to the 2n plus 1 over quantity 2n plus 1 factorial plus dot dot dot. Okay, what's that? This that we just wrote right here is actually this. So what we just showed was that given that this is true, so you have to believe that this is true, but if you do, the sine of negative x is equal to the negative of the sine of x, and you were done. So that's the symbol that you sometimes make when you were done. Like in geometry, you would make a box. I always make a box and then I also fill it in. You don't really need to do that. But this is a much more algebraic proof. It uses the concept, right? F of negative x equals negative f of x. We could do it for cosine too. I'll do it. I know that this is going to be a long video, and I apologize, but cosine's a little easier because it's even. Even functions in general are just easier to prove because you basically like go through and kill all the negative signs. Let's see, 4 factorial plus. So you can always put a plus there, even though it's weird, right? You always just, like, it should by the pattern be minus, so maybe you would prefer that. Maybe I should do that. But trust me, when you get to Calc 2, you're not going to care about that. And then plus -1 to the n, x to the 2n over 2n factorial, but you got to put the parentheses. Okay. So cosine of negative x is going to be 1 minus quantity negative x squared over 2 factorial plus quantity negative x squared to the 4th. 4 is the easiest. If you accidentally make a 2, you can turn it into a 4 so easily. And I do that a lot. So that's why I'm so happy to know that. Plus -1 to the n, negative x to the 2n over quantity 2n factorial plus dot, dot, dot. So here you can see cosine of negative x is 1 minus negative x squared is just x squared. So x squared over 2 factorial, and then plus negative x to the 4th is just x to the 4th. So we're just kind of like squashing all those negative signs that thought they were there. And it's going to happen here, where we just get x to the 2n over 2n factorial. But this, again, this thing that we just ended up with here, all of this is the same as all of this. So that's actually just cosine. So cosine of negative x equals cosine of x. Therefore, even. Even is like always a little bit easier to deal with. So the one thing I did want to mention that, so sine is an odd function, and you only need odd powers over odd factorials. It's like super nice that whoever they are, that they worked it out so that math would work this way. And then cosine is even, you only need the even powers over even factorials. Like, these are very complicated series, but they're not. Like, they could have been so much worse, and they just aren't. So I think I'm just going to finish this page because, I mean, why not? Because we're like almost done. So sine root 2 over 2, root 2 over 2. So sine is odd, so negative root 2 over 2. Cosine's even, so it'll still be root 2 over 2. Tangent is 1, and then tangent is odd, so this will be negative 1. 5 pi over 6. Sine. So it's always weird. Like, you should fill in the cosine first. It just makes it easier. Sine is odd. Cosine is even. Tangent of 5 pi over 6 is negative root 3 over 3. Tangent is odd, so this will be root 3 over 3. 4 pi over 3, so the cosine is negative 1/2, negative root 3 over 2. All right, sine is odd, so this will be positive root 3 over 2. Cosine is even, so it's going to stay negative. Tangent of 4 pi over 3 is root 3. Tangent is odd, so this will be negative root 3. So that's one of the ways you can really quickly use even and odd. You got to know them. The series thing is just really cool. I wanted you to know that, to see it. It's going to come back later in your life. It's going to come back later this year, in fact. You know, having some sense of this, I think, is a really good idea, because going forward, like, you ever wonder how your calculator does it? Your calculator does not do this. Your calculator uses something called Cordic. That's an I. So you could look that up if you're interested. But it could have used this. This is just a little, as far as computers go, this is a little less accurate and a lot slower, as I understand it. But I also don't really understand it. Cordic is like a computer sciencey thing, and I'm not super up on that. But anyway, that's this page in the notes. I'm going to cut it here. I will see you in the next video where we do some more stuff. So see you there.